Alright, so in this video today, we're going to be looking at three different problems in which we try to find the volume of some solid. Now, the setup for each of these problems is going to be a little bit different, but what we're going to try to emphasize is that the process you need to go through to solve these problems is all pretty similar. Okay, so let's start with this first problem, in which we're asked to find the volume of the solid whose base is the region under the curve f of x is equal to the square root of 9 minus x squared, and whose cross-sections are squares perpendicular to the x-axis. Now, a good first step in all of these problems is to go ahead and kind of sketch out what's happening on a graph. So you'll see I've already drawn on the graph here our curve f of x is equal to the square root of 9 minus x squared. And I've also already drawn in a couple of the cross-sections. Now, these aren't perfect, obviously. They don't need to be. They don't need to be when you draw them either. Okay? The idea is just to get an idea of what's going on here, to sort of visualize this solid that's going to be formed and the cross-sections of this solid in particular. So you'll see here I drew a couple of these squares. They're actually rectangular prisms because they have some little bit of thickness. For more information on why we do that, I'd refer you to our other video we have on finding volumes of solids. But in this one, we're just going to look at how to attack this problem, or how to start this problem. So you'll see we have these cross-sections drawn in there, and you'll see that I have the length of these cross-sections, or the height of the squares here, drawn in red there, and I labeled it L. And so the first thing we need to ask ourselves in all these problems is, what are the areas of each of these cross-sections? Because if you look at our formula we have written down there, where volume is equal to the integral from a to b of a of x dx, we need to know a of x, and we also need to know the bounds of our integral, our a value and our b value. And so that a of x is usually the trickiest part of these problems. Okay? So let's go ahead and look at the first question we need to answer, which is, what are our cross-sections? Now, in this one, identifying the cross-sections is pretty easy because they tell us that they're squares perpendicular to the x-axis. Okay, so we don't have to think too hard on this one. When they say, what are our cross-sections, we can answer right away, well, those are squares. Right? And we know that our area of a square in general is the length squared. Now, look at the drawing here and look at these cross-sections. And notice that the heights of each of those two squares I have drawn, or the rectangular prisms I have drawn, are different. This is because the length, or the height of these squares, is going to vary depending on where you are on the x-axis, right? It's not constant along the x-axis. And so our length here is going to be some function of x. And you'll notice that the length there is the top of our curve, f of x is equal to the square root of 9 minus x squared, down to the line y equals 0, or the x-axis. And so it's a pretty safe bet here that we're going to take the top minus the bottom, which would just be our function minus 0. Okay? So our length in this case is the square root of 9 minus x squared. So when we go to write a of x, it's going to be the length, which we just identified as 9 minus x squared, because remember it varies with respect to x squared. Okay? So this is the, in our case right here, for this particular solid we're forming, this is the area of each one of those cross-sectional squares. So then the last step here in setting up this problem is to go ahead and just write the volume. So we have an integral in which we're going to write the bounds here in just a second. But we know our a of x now, we just identified as the square root, 9 minus x squared, dx. And the bounds of our integral you can see pretty clearly if you sketch this out there. It goes from negative 3 to positive 3. So our bounds there are negative 3 to positive 3. Okay? So again, the hardest part of most of these problems is identifying what is the area of our cross-sections dependent on x. But if you draw out the situation here, it's a little easier to see. Okay, so let's go ahead and move on to the second problem. And in this problem, you'll see that we're trying to find the volume of the solid generated by revolving that same area we just had. So the area under f of x is equal to the square root of 9 minus x squared, about the line y equals 0. So here they're not telling us our cross-sections right away. They're giving us some base area and telling us to revolve it about the x-axis. Okay? So I have a rough sketch down there again. And again, it's not perfect, but it doesn't need to be. We're just trying to get the idea of what's going on here. Okay? And I've drawn in a couple of the cross-sections, which, as you can tell, are going to be disks in this case. Okay? And they, again, have some arbitrary little thickness. That's not really what we're concerned about here in this video, though. We're just concerned about finding the area of any one of these cross-sections, these two-dimensional cross-sections you could think of. Okay, so you notice I have the radius of each of these disks labeled on there, and you also notice that the radius of these two disks in particular that I drew are different. So it's a pretty good bet again that our radius in this case is going to vary with respect to x. Okay, so again we need to ask the question here, what are our cross sections? And as you can see from the drawing, and as you might be able to guess from any type of revolution about any line, our cross sections here are going to be disks perpendicular to the x-axis. Okay, go ahead and say we got a disk. And then we have to think about what is the area of a disk in general. Well, it's going to be pi times r squared. But again, looking at our drawing here, and also just thinking about what the radius of each of these cross sections is going to be, we know that r is going to vary dependent on x. So again, we need to think about what is r as a function of x. Well, if we look at our drawing, we can see that we go from the top of our curve, which is f of x is equal to the square root of 9 minus x squared, down to 0 for each of the radius. Okay? And so that is a pretty good bet for what our radius is going to be. So in our case here, a, dependent on x, going to be pi. Now our radius, like we just said, is the square root of 9 minus x squared down to 0. So you could put minus 0, but obviously that's not going to change anything. And then squared. So that is our area of each one of these cross sections as a function of x. Okay, so then the last step, again, is to find the volume. We're dealing with the same base area here, so it's a pretty good bet, and as you can see from the drawing as well, that our bounds of integration are going to be the same, -3 to +3. Okay? And then our a of x we can just plug in. That's what we just identified in this last part. Square root of 9 minus x squared, all squared, and dx. Okay, so this looks like a completely different problem at first glance, right? We're no longer given the cross sections. They're telling us to revolve something about the x-axis. But the process to find this volume is exactly the same. We identify what are our cross-sections, we identify the area of those cross-sections in terms of x, and then we plug it into our formula for volume. Okay? And we're not concerned in this video about where this formula for volume comes from. That's the focus of our other video on volumes. This is just tackling how do we approach each of these different looking problems. And the answer is that we approach them all the same way. We look at cross-sections. So with that in mind, let's go ahead and look at our third problem now. This one's a little bit trickier because we're going to have a gap in our revolution. So we're taking basically our same base area here of the square root of 9 minus x squared plus 4, and then, of square root of 9 minus x squared, and we're shifting it up 4, as you can see from the drawing. We're taking the area between that curve and y equals 4 and revolving it about the line y equals 2. So this is one where it really helps, I think, to sketch it out, as you'll see I did over there on the left-hand side of your screen. And you'll see that I also sketched in a couple of the resulting cross-sections. So we're revolving again here. So we know we're going to be dealing with some type of disk shape, but there's a big hole in the middle of it from the hole in our revolution. And so we're going to be dealing with washers in this case as our cross-sections. You also noticed I drew in the inner radius of this washer and the outer radius of the washer for each of these two cross-sections. That's going to come into play when we try to find this area. Okay, so again, we ask ourselves exactly the same question to start. What are our cross-sections? And as I just answered, and as you can see from your screen, as will be the case for any type of revolution with a gap, we're going to be dealing with washers. So then we have to ask ourselves, what is the formula for a washer in general? And the answer to that question is the area of the outer circle, so pi times big R squared, minus the area of the inner circle, so pi times little r squared. So once we have that written down, we can think about what are we trying to find? Well, we're trying to find big R and little r. And as you can see from the drawing we have over here, big R is going to vary with respect to x. It's not constant. But as you might be able to guess by looking at that drawing and thinking about what these cross-sections are going to look like, our little r should actually be a constant here. Okay, so if we look at our big R, we're going from the top of our curve at f of x down to the line y equals 2. Right? You can see that pretty quickly if you draw this out. And so our r of x here in this case is going to be equal to the top of that curve, which we know is just our function, 9 minus x squared plus 4, down to the line y equals 2, so minus 2. So we find that our r of x value is the square root of 9 minus x squared plus 2. Okay. Now our little r value, we'll put r of x, even though we know or we have the intuition that it's probably going to be a constant. But our little r value here goes from the sort of bottom of our region up there at y equals 4 down to the line y equals 2. So 4 minus 2 means our inner r value is not actually a function of x, it's a constant 2. Okay, so now when we find our a of x value, we have a of x is going to be equal to pi. We just found r of x, or r value, square root of 9 minus x squared plus 2 squared minus pi times our little r value, which is 2 squared. Okay, so that was the trickiest part of this problem, definitely, is finding that a of x value. And now we can go ahead and find our volume. It's going to be the integral, and again, we're dealing with the same sort of region here, this semicircle. So we're going to be going from -3 to +3 again. And you can see that pretty clearly by looking at your drawing that you make, or by looking at my drawing that I made. And then we just plug in our a of x value we just found. Pi square root 9 minus x squared plus 2 squared minus pi times 2 squared. Go ahead and put that all in parentheses so that I can throw the dx out behind that. Okay, so 3 very different looking problems to start are actually made a lot easier by just identifying this sort of pattern we can follow. And that pattern is identify the cross sections, use that to find the area of those cross sections with respect to x, and then integrate across whatever our bounds are.